Hello. So, as promised, today we are going to, or tonight, we're going to implement ResNet18 from scratch and compare it. Well, we'll see how far we get, but I'll try to launch a training on Runpod and see if I can get the convergence to some kind of validation accuracy. But I may just end up coding the model and testing it locally, and then calling it a night. I'm pretty tired. It's 11:30 p.m. right now, but I feel eager to kind of get this out. So let's um let's get started. Remember, the premise is we started with the vision transformer, which is a data hungry translation invariant model that is position unaware and makes no assumptions about the data, and any anything it learns anything it learns about the data, it learns directly from the data, as opposed to a traditional convolutional neural network model, or a model that uses kernels or feature extractors that has inductive bias because it makes spatial assumptions about your data, such as, you know, elements in the image that are closer to each other are more likely to be higher relate or more likely to be related, right? That's why you can make a face that's composed of eyes and of ears, right? These sliding feature mappers um, have a spatial proximal element to them that makes the assumption that elements that are closer to each other are more related. That's how it builds these higher, more abstract feature maps. And again, it's not a bad thing. It's why these models can work on um, less complex data sets and data sets with um, less data points. So yeah, let's get started building ResNet18. We're also going to use the custom modules that I built last time. I realized also that I forgot to implement batch norm, so we're going to do that as part of this video as well. So I created a new repo, ResNet18. So I'll include that in the link in the description as well. So let's get started. Um, okay, so mvim resnet 18.py. Yes. Pretty tired right now. Let's see how well I do. If I don't do well, I'm just going to call it a night. Import torch. So, okay. This is the architecture. We're going to create these layers. So a block is going to be one convolutional block. It's going to be convolution, batch norm, and sometimes the activation function. Jesus Christ. But it's always at least going to be a conv and a batch norm. That's going to be one of these blocks right here. I'm going to, sorry, one block is going to be these two. I'm going to call this a block. I'm going to call this a basic block. This is your basic ResNet block. And what it does is your basic ResNet block um, slides feature mappers over your image, and sometimes it downsamples your image at the same time. So essentially, it's going to either essentially, as the layers get deeper and deeper, we're going to continuously increase. Well, we're going to continuously keep you know, we're gonna we're not going to increase the stride, but the stride is going to stay 2 at the beginning of each of these blocks. So we're going to see, the model's going to see more and more of the image, and also as the stride is 2, the number of channels is going to increase. So we're going to see less details, like less pixels per computation, and or we're going to skip. Yeah, we're going to see less pixels per computation of a feature, right? And we're going to assume that these are higher level and more abstract features, so we don't need to see as many pixels, right? So we're going to stride over this image at a number of 2 as the layers increase, and we're also going to increase the number of feature maps. And then we're going to have these residual connections, which means this is the identity getting passed. So we fork off here, we do some computation, we compute some feature maps, and then we add the identity back to the, well, we do some computation to the identity to make sure the shape can, we can project whatever computation we did here in this path, in the computational path, we projected the original image into some other embedding space, some feature mapping space. Then we need to project the identity into that same space. And then we add it together. This is so that, again, I know I keep saying I need my iPad, but once I have my iPad, I'll be able to explain these things much better. The idea is that instead of learning an entire transformation, we're going to learn a residual of a transformation. So instead of learning f of x entirely, we're going to learn x plus f of x. So that means we don't have to learn. That means like we can just learn a residual of a transformation. We can continuously learn residuals and adding them to the identity as opposed to having to learn an entirely new transformation. The reason why this is beneficial is because what if we have this. So with ResNet, what happened is ResNet, this is around the time where people started discovering that if we just make convolutional networks really, really deep, then we can increase our accuracy. But they started running into the vanishing gradient problem. And this is because this is related to what I'm saying. Like, if you're trying to learn an entire transformation f of x, but you have a really deep neural network, chances are at several stages in that network, the transformation that you're going to learn is going to be really small, right? You're not going to learn much of a transformation. It's going to be like close to the identity, right? And so that means that the learnable weights of that transformation are going to be really, really small, which means that the gradients that pass through there are going to be really small. And if you have a few of those, it doesn't take much, right? If you have 0.001 times 0.001, that's multiplied, that's 0.0000, right? It magnifies quickly. And if you have a few of those very small learned transformations, you're going to run into the vanishing gradient problem. But if you learn residuals, meaning if you take the identity and just learn a residual and add it to the identity, and you keep learning these residuals, if the residual transformation that you learn is very small, you still have the original identity path for the gradient to flow through, right? That's how it solves the vanishing gradient problem. So I'm going to make a function called make layers that uses basic block. So basic block is going to create 2 of these right here, right? These 2 right here. And then make layer is going to call basic block, and it's going to stack 2 basic blocks together with one identity added here and another identity added after the second block. And then we're going to make 4 layers. I'm going to call make layer 4 times, and then I'm going to have the beginning of ResNet18 and the end of ResNet18, which is a average pool plus a fully connected layer. The beginning of ResNet18 is a convolution with kernel 7, stride 2, and padding 3. Same padding, so padding 3. And then it goes to ReLU, a batch norm, then it goes to ReLU, then it goes to max pool, then you pass it through your 4 layers. You go to average pool, you flatten it out, and then you pass it into a fully connected layer that gives you logits per your number of classes. In this case, we're going to do CFAR10. Well, first let's do MNIST just to make sure that we can get good accuracy quickly, and then we'll go to CFAR10. So let's do this. Where am I? I'm in the camera. Cool. I'm going to start sweating any moment now. It's nighttime, but it's still hot. I should use a different. It's okay. We'll use the same environment. It's fine. Should be fine. All right, let's keep starting with the basics. If main is our main function, I always do the same. Don't ask me why. I just like it like this. Okay, I'm going to do our data class. I think we need that. For MNIST, CFAR10, we need 3 color dimensions. What do I want to do now? I want to do basic block. So I'm gonna make a class that spits out these two. Spits out the input in this, and then added to the identity. Passes through these two convolutions and adds the identity. Kernel and the padding we'll set on the inside. The kernel will always remain the same. So it's going to be conv1, dash norm1, relu, conv2, dash norm2, and then x equals x plus identity. So that's the flow. So conv1, so our NN modules is in there from modules. NN modules. So we have everything except batch norm. So we'll have to implement that. Okay. Self conv1 equals conv 2D in channels, out channels, kernel IO KSP, kernel size equals 3, stride equals stride, right? So the first stride we're going to pass in, it's going to be 2. It's going to be optional. We're going to set it to 2, but the first time we come into a block, a layer, which is comprised of 2 blocks, where each block has 2 convolutional layers, right? The first time we pass into a layer, we're going to downsample by increasing the stride, and we're also going to increase the number of features. So the assumption is, in order to create more abstract features, we're concerned with less detail, and we want to see more of the image. We want to see more of the image with less information. I don't know. We want to use less information we need less information to create more complex or more abstract features, if you will. Stride KSP padding equals 1. Dash norm equals. We'll have to, well, for now, let's use the default one just to get it working, and then we'll code up our own. I just want to make sure that I can call the interpreter and see if there are any syntax errors. Out channels, we're gonna normalize over the number of feature maps. Self.relu equals. I also realized in the vision transformer and my transformer, I used relu instead of relu. I don't know how you say them. I should know this. I literally should know this. I hear people saying different things, but I should use GelU instead of RelU. I like RelU and GelU. It sounds better. Am I still on the camera? Yes, I am. Okay. Conv, batch norm, RelU, conv2. Oh, yes, conv2. Let's compile this. In channels, out channels, stride. $49. Right. Okay, well, that works. Okay, and so it's going to be out channels, goes to in channels, out channels. So the first block increases the number of feature mappers and increases the stride. So it sees more of the image and less information. The second block, basically it doesn't change the kernel size, doesn't change the stride, doesn't change the number of features. It simply just refines. It basically just refines what we did. And the first block changes the stride and the number of features from the layer before. The second block refines, is like a refiner, feature refiner. Kernel size, stride is 1, padding equals 1. Batch norm 2. And then that should be it. All right, and then we need to do downsample if self.downsample is not none, downsample equals none. If self.downsample is not none, wait, hold up, no, hold on, no. If stride, right, if the stride is changed or in channels, right? Then self dot down. Then we need to change. Then we need to pass the identity through a transformation. So that the transformation is going to be, so basically we're going to assume the stride changed or the channels changed. So if the channels change, that means we need to send in channels to out channels. Boom. And then kernel size is going to be 1 because we're not going to, it's an identity preserving mapper. So we just map pixel to pixel. And then the stride is going to be equal to whatever the stride passed in was, kernel size stride, KSP. Padding is going to be 0, right? We're not going to add any padding because the kernel size is an identity map. The kernel is an identity mapper. Am I still in the image? Okay, doing well. And then comma, out channels, and then pass it through a batch norm. Else self dot down sample equals none. How are we doing? Okay. How are we doing here? Okay. Okay, now forward. So identity is x, x self dot conv 1 x, x receive self dot bash norm 1 x, x receive self dot relu x, and then that was the first. So layer, first block, first conv layer. Now second conv. I guess you would call this a residual, a transformation, residual transformation learning. Yeah, I don't know what you would call this. You have layers and then blocks and then whatever is less than a block. Self.conv2 x self.bashnorm1 x, and then that's it for that. So no nonlinear activation, but we do add we do if self.down sample is not none, self.down sample identity, and then x plus equals identity. Okay, here you go. We take the identity, we learn some transformation. If the transformation projected the input to another space, we have to project the identity to the same space. Then we add it to the learned transformation. We add it to the learned transformation, and then we return x. So I just wanted to mention quickly, there's supposed to be a relu after this identity. In my original video, I forgot to add this ReLU. I don't know why I said there wasn't, but there has to be nonlinear activation. I mean, that's the whole point of, I mean, stacking linear models together is just a linear model. So you have to add, the whole power of neural network models is adding nonlinear activation. So make sure you add this line here. Okay. Now, let's make ResNet18 self num classes. We don't need to make those on separate lines. This is going to be conv1, which is kernel size 7, stride 2, padding 3, dash norm 1, ReLU, max pool, layer 1 through layer 4. Average pool, flatten, linear. So your logits, num classes. Okay, let's give this a shot. Let's give this a shot. Okay. ResNet18 self.conv1 equals conv2d IOKSP in channels, out channels, kernel size, stride, padding. There are no biases in this. Maybe there are, but in this educational, I guess, implementation, we'll say there are no biases. Am I still in the camera? Yes. Stride 2, kernel size 7. So this way we take in a lot of the image. Like your first transformation is going to your first transformation is going to see its kernel is going to take in a lot of information. In channels, out channels, it's going to be 64 just by the design of ResNet18. Dash norm 1. Out channels is 64. ReLU. Max pool. This is our implementation. Kernel size 3, stride 2, padding 1 by the design of ResNet. So we are reducing the spatial dimension. We're reducing the spatial dimension of the image, right? Okay, and then we need to make our layers. So remember, a layer is 2 blocks. 1 block, this is 1 block, this is another block. A layer, which we made our basic block already. Now we're just going to make a function called makeLayer that stacks 2 blocks together. So layer self.layer1 receive self.makeLayer in channels, out channels, and blocks. The number of blocks, stride. For the second one and on, the stride is going to be 2 by the design of ResNet18, right? To see increasingly more and more of the image as our features get more and more abstract. In channels 64, maybe I'll just leave this. On channel 64. This is by the design of ResNet again. Okay, so def make layer self make a layers list, and then we'll append a basic block in channels. We'll pass in channels, out channels, and we'll pass in stride, right? So the first block is always going to increase the stride, and for in range actually I write everything out for the muscle memory. Jiu-jitsu, baby. Stride equals 1. This is out channels, stride equals 1. Return. Boom. So this line, in channels, out channels, creates our first block. And then we append our second block, out channels, out channels. So here, in channels, a better example is the second layer. In channels 64, out channels 128. So from this layer, we'll have 64 feature maps, 64 channels. So the in channels will be 64, and we're going to expand it to 128. And the stride is going to be a stride of 2. So that means that we're definitely going to have to downsample our identity. We're going to have to project our identity into the same feature mapping space as the input, because the stride and the channels changed. As opposed to the first one, only the channels stayed the same, only the stride. Actually, the channels stayed the same. Yeah, everything stays the same, so there will be no downsampling. Just a refining of features. Layer 3. 256, 128, 256, 512. Now we need self.average pool. One. So it's going to just average the entire feature map. So if you have 20 feature maps, it's going to take the average of each feature map. So if 20 feature maps, you're going to have 20 singular values, which is the average of each feature map. Fully connected equals linear 512 to num classes. So we'll make layer forward X receives convolution, X receives now we're going to call each layer. And now X receives self.average pool. This will give us batch 512 one by one. I think it'll be one by one. Should be one by one. Should be one by one. Maybe it isn't. Maybe it's actually batch times 512. Torch dot flatten. I think it's just b by 512. X first dimension, which is the 512th dimension. So we'll flatten each. Yeah. And then we'll send it through. Let's see if we have any syntax errors. 95. Yeah, I didn't pass config in channels. Right. Can't call named parameters. Okay. No interpreter errors so far. So let's make the data set MNIST. Root equals root equals yeah. So let's make the transformation pipeline. Let's make it really simple. Oh, what just happened? Normalize shape. Let's just see if this runs. Mean standard deviation. What are we gonna do? We need to config p-train split times length data set train split random split. We need to split our data set up. Data set train split length data set minus train split train test data loader train batch size shuffle true for train. Train data loader test data loader. Model optimizer torch.optim atom w again parameters learning rate float. It's a little aggressive, but that's okay. That is fine for now. It's not standard. Boom. What am I doing? What else am I doing? TQ with TQDM. What am I doing with TQDM train DL? SPBar for inputs, labels, and PBar. labels, receives inputs. Where am I? Is the video even recording? Good. Oh, knocked the power out. Oh, it's 12:16 a.m. Getting tired. Gonna power through. Going to power through to device labels. Okay. Let's just break and see what happens. Is it still recording? Yes. Not really sure. By the way, I was expecting it to be CFAR10. It's MNIST, so it's not 3 dimensions for RGB. There's not 3 color dimensions. It's only 1. See, it's CUDA if torch.cuda.is available else CPU seed 1337 torch manual seed. Okay. Let's see. I was told by someone that I need to make the text bigger, and I apologize if I haven't done that for the whole video. I need to add that to my notes and make sure I stay on top of that each time. Would like to hear comments about how small is too small. Is like that good? I don't really know, to be honest. Okay. We are now doing our standard PyTorch training. Criterion cross entropy loss criterion outputs labels loss loss dot backward optimizer dot step total loss. Let's tally up some things. Train loss dot item. We're gonna average it times puts dot size times the batch size. Predictions we're going to get from the outputs, which is going to take the max of the logits. We don't even need to standard to normalize. train correct is reds equals labels sum, count them up, item, total, accuracy. Okay. See what happens. Assuming this entire network was made correctly in one go, which would be highly unlikely. But if we get good test accuracy, then yeah, let's pause the video. Okay, this is taking a really long time. Let me, it's MNIST. Let me, let me just decrease the amount of data. That's pretty good. Let's do some validations to make, we need to make sure that this is all running correctly. Train val replace. Okay, this needs to be eval. PyTorch.no-grad. It should converge to a pretty high validation accuracy pretty quickly. Let's pause the video. Oh, okay. Looks like good. Okay, now let's pause the video. Yeah, so it's still going. It's on the third epoch. We can see it's increasing. Let's see. It seems to be slowing down. Interesting. This shouldn't be happening. Something is awry. Something is awry. Looks like that's a problem to fix for tomorrow because I am very, very tired. But it looks like we're kind of on track with ResNet. I mean, it looks like the architecture is basically correct. There's something weird happening. There's something accumulating here that I'm not sure of. I'm not sure what's accumulating here, but it shouldn't be slowing down in the way that it is. Shouldn't be slowing down in the way that it is. I'm gonna go ahead and check this out. Yeah, it's like slowing to a halt. Something's wrong. Something's wrong. Gonna have to check that out. We'll leave that for tomorrow. But yeah. The validation accuracy and training accuracy should be closer as well at this point. Validation accuracy should be close to 90, I think, around now. So yeah, let's stop this here and we'll debug what's wrong tomorrow. But this is the basic ResNet. I feel good about this. I like this architecture. I'll just have to go through it with a close eye and make sure I find what the issue is. ResNet18 for video. Anyways, thanks for watching. We'll continue this tomorrow. I'll find what's slowing it down in these successive iterations. Some kind of build up. Probably something with torch that I didn't set. Maybe with the gradients, I don't know. But anyways, I'll figure out what it is. We'll get I know that we'll get 90%, 95% accuracy on MNIST, and we'll switch to CFAR, make sure the validation and training accuracy, progression looks the way we want it to, and then we'll put it on Runpod, and we'll get it to converge to 85% accuracy. We'll see if it converges to a better accuracy quicker than a vision transformer, which theoretically it should. So tomorrow. Thanks for tuning in. Good night, everyone. Hey, everyone. Just back from last night. Remember the model started getting bogged down. ResNet18 started getting bogged down after successive epics for some reason. I figured it out. I'm calling batch norm 1 twice in basic block. So basic block, this needs to be batch norm 2. Yeah, batch norm 2. That's the mistake. So if you look, when we run Python ResNet, you'll see it converge to very high validation accuracy really quickly. I wonder, did I remove? No, it's still training on a subset of the data, which is still fine. Well, actually, no. Let's have it train on the whole data. Validation accuracy 94. You can see it's really high. Let's have it train on the entire data set. There you go. Let's pause this.